So our next example will mean revisiting an older example. We had this example earlier with the New York Yankees and New York Mets, their duopoly, and we established that depending upon what the other team is charging, that's going to influence what price you will charge. So there'll be four possibilities here. So first of all, both you guys charge the high price. So you charge 605 and they charge 400. We established earlier that 605 was the best response to the price of 400 in our last episode. Alternatively, you could pick your high price and they charge their low price. You could both play a low price, or you could play low while they play high. So with this demand and this marginal cost and this total cost function, go ahead and calculate your profit for each of these four scenarios. So go ahead and pause the video here until you've worked through that problem. When you're done, press play and we'll go through the solution. Alright, presumably you've solved the problem by now. First of all, quick side note. Some of you guys may have taken calculus already. If you have, you can verify that the marginal cost function over here is the derivative of the total cost function. But if you haven't taken calculus, don't worry about that. Anyways, moving on. We're going to look at our four cases and calculate our profit for each of those cases. So case 1, I charge a high price of 605 and the rival team charges their high price of 400. So we plug that into demand to figure out what quantity is going to be. So our price is 605, so we have 605 equals 1,000 plus 0.5 times their price of 400 minus 0.1Q. What does that work out to? Half of 400 is going to be 200, so we have 1,200 over here. 1,200 minus 605 is going to be 595. Then you can push the 0.1Q to the other side, and you have 0.1Q equals 595. So to isolate the Q, or perhaps I should say in these times to quarantine the Q, you could divide both sides by 0.1, and that gives you Q star, the optimal Q of 5950. So now we found quantity. Let's calculate total revenue. Multiply that quantity of 5950 by the price 605. That comes out to about 3.6 million. To find profit, you gotta subtract off total costs. Total costs are, we said, 10 times Q. So if Q is 5950, then total costs are going to be 59500. So that comes out to, looks like 3.54 million. So that's case 1. That's what happens when we charge 605 and they charge a price of 400. Now move on and look at case 2. So case 2 is we keep charging 605, but now they are charging 200. What's going to happen there? So you plug into demand, so we have P equals 605, so we have 605 equals 1,000 plus 0.5 times P other is 200 minus 0.1Q, so that comes over here. 1,000 plus half of 200, half of 200 is going to be 100, so this comes out to 1,100. 1,100 minus 605 is going to be 495. Then I'm going to push the 0.1Q to the other side, so I have 0.1Q equals 495. As before, we're going to quarantine that Q by dividing both sides by 0.1, so that Q is isolated on one side of the equation. Then we get Q star is 4950. So you can check your intuition here. When the other team cuts their prices from 400 to 200, that's going to reduce demand for our team's tickets. So when the other team has a low price, we're going to sell 4950 tickets. Back on the earlier slide, when they charged a high price, we sold almost 6,000 tickets. So it matches your intuition. Cutting prices is going to steal demand from the other firm. So now calculate total revenue. That's price times quantity. So our price is 605. You multiply that by Q star of 4950. That comes out to a little bit under 3 million. Next step, we gotta find cost, because once you put cost and revenue together, we find profit. We said total costs are 10 times Q, 10 times 4950 is gonna be 49,500. So now profit's gonna be revenue minus costs. That works out to about 2.9 million. So now I finished the first two cases. We'll look at case 3 now. So the other possibility is that we charge a price of 555 and the rival team is charging a price of 400. Same process. We're going to plug these numbers into the demand curve to find quantity. So P equals 555 is going to go over here. 555 equals 1,000 plus 0.5 times 400. Audience price is 400 minus 0.1Q. 0.5 times 400 is going to be 200. 200 plus 1,000 is going to be 12,000. 12,000 minus 555 is going to be 645. We can move the 0.1Q to the other side, and we get this. Then we quarantine our Q by dividing both sides by 0.1. That's equivalent to multiplying by 10, so now Q star is going to be 6450. Again, this does match our intuition. Compared to the other cases, our price here has gone down. So back before, we were charging 605. Now we're charging a lower price, 555. Unsurprisingly, when you cut prices, you get more customers. So quantity rose from being around 5,000 to now being above 6,000. All right, let's find total revenue. That's going to be price times quantity. Our price is 555. Quantity is 6450. That's going to come out to around 3.6 million. Now, because we have more customers, we also have more costs. Total costs are 10 times Q, 10 times 6450 is going to come out to 64,500. So now if you look at profit, that's going to be total revenue minus total costs. That's going to be about 3.5 million. All right, we have one last case to look at. So last possibility is we charge 555 and they charge 200. Same procedure as before. You plug this into demand. So demand is going to be 555 is 1,000 plus 0.5 times 200 minus 0.1Q. So that's written down here. Half of 200 is going to be 100. 1,000 plus 100 is going to be 1,100. 1,100 minus 555 is going to be 545. To solve for Q, we got to quarantine the Q. Let's first push it to the other side of the equation. So we got 0.1Q is 545. Lastly, to complete the isolation of the Q, we divide both sides by 0.1. That gives us Q star of 5450. Again, check your intuition. So when the other team is charging a lower price, that's going to take some demand away from our team. Some fans are going to start going to their games instead of watching our games. So when their price is lower, demand for our firm should also be lower. And the quantity of tickets we sell here, when they charge a low price, is going to be smaller than the tickets we sold back when they charged 400. So again, you can see competition at work here. When the other team cuts their prices, it's going to reduce the number of tickets that we can sell to our fans. Alright, let's find revenue. That's price times quantity. Price here is 555. Quantity we established is 5450. That comes out to around 3 million. Total costs are 10 times Q. So if Q is 5450, 10 times that is going to be 54,500. If you find profit by doing total revenue minus total cost, you get a number that's a little bit under 3 million. So here's what we figured out. Just summarizing our last couple of slides. We estimated profit for each of these 4 scenarios. In order to use game theory, we also have to know what is the other team's profit. So our economists do some math and they go estimate what that is going to be, and that's going to give us a game that we can start looking for dominant strategies and start trying to find Nash equilibria. So our economists go to work, they do the same kind of procedure, the same kind of math for the other team, and let's say this is what happens. So when our team starts a high price of 605 and the other team picks their high price of 400, we'll call that high, and we said that means your profit is going to be 3.6 million. So in this table I'm showing a payoff of 3.6 for you to correspond to that. Now if you pick the high price of 605 and they pick their low price of 200, then your profit's going to be about 2.9 million. So in the table, the price of 605 is your high price, so in this row, the price of 200 for them is their low price, so they're going to be in this column, so that's this cell. We established that our profits there are 2.9 million, so I'm putting 2.9 for your payoff. Let's say our accounts did the same work for the other team, and they estimate that the other team's profits will be 3.5 million in that case. For the rest of our table, case 3 was if we pick our lower price of 555 instead of 605, and they pick their high price of 400, our profit's going to be 3.5. So our low price and their high price correspond to this cell. Our profit is 3.5 in that case. So that's why we have a 3.5 here and a 3.5 over there. Let's say their profit is going to be 1.5. Last scenario, we pick our low price of 555. They pick their low price of 200. Our profit there is going to be 3 million. So low is this cell. So 3 million for you. Let's say it corresponds to 2 million for them. That's the setup of our game. So your mission, go ahead and look for a Nash equilibrium and look if there are any dominant strategies. So pause the video here until you work that out. When you're ready with your answer, press play. Alright, I'll assume you have figured out the problem by now. So let's see what's going on. I'll start by looking for dominant strategies. I'll start by looking at things from your perspective. So let's say you think the other team is going to pick the high price. So if they're picking high, you're going to be in this column here. If you pick the high price too, your payoffs here are in red, so you're going to get 3.6 million in that case. Now, if they're picking high but you're picking low, we're going to be in this cell down here, your payoffs are in red. Remember, you're in red, so you're getting 3.5 million in that case. Which is better? Well, you want to have the biggest possible profit, so you'd rather play the high price if they're also going to play the high price. Now suppose instead you think they're going to play the low price. So if they play low, we're in this column. If you play high, that's this row. So you play high, they play low, that's going to be over here. That means your profit's going to be 2.9 million. But if you both play low, then your profit's going to be 3 million. Again, you're trying to maximize your profits. So if they're playing low, if you think they're going to play low, then you want to play low as well. So for you, there is no dominant strategy. If they're playing high, we established you want to play high. But if they play low, you want to play low. So what you want to play is going to depend upon what you think they're going to do. There's no one strategy for you that's just always the best. So you don't have a dominant strategy. Now I'll do the same analysis from the other team's perspective. Like I said before, not all games are symmetric, and this game is not symmetric. That means we got to do the analysis separately for the other team. We can't just assume that what holds true for you is going to hold true for them because the game is no longer symmetric. Alright, so from the other team's point of view, suppose they think you're going to play high. If you're playing high, then we're going to be in this row of the table. If they also play high, they're going to be over here. So high is this cell. Their profits are in blue. That's what they care about. They get 3 million in that case. Now if you're playing high while they're playing low instead, their profits shown here in blue are 3.5 million. Just like you, they want the biggest possible profits. So if they think you're playing high, they'd rather play low and get 3.5 million rather than get just 3 million. So if they think you're going to play high, they want to play low. That's what we've established. The other possibility, what if they believe you're going to play low? If you play low, we're going to be down here. So if they play high, we're going to be in this cell. This cell corresponds to they play high, you play low. In that case, their profits in blue are 1.5 million. If they play low instead, now you're both playing low, their profits would rise to 2 million. They want to play low because that gives them the bigger profits. So what we've established is that if they think you're going to play low, they want to play low. If they think you're going to play high, they also want to play low. So no matter what they think you're going to do, they're definitely going to play low. So that means low is going to be a dominant strategy for the other team. Like I said before, this game is asymmetric. You don't have a dominant strategy, but they can still have a dominant strategy. So now you know the other team's definitely going to play low. We showed earlier that if they're playing low, you will also play low, so we're going to end up over here. Both teams are going to pick the low price. So like I said, with Nash equilibrium, if besides pursue their dominant strategies, that can be a Nash equilibrium, so low is going to be it. Let's just verify. So once again here, you see this situation where it's a cooperative outcome, both sides playing the high price, but that's not Nash equilibrium. So you can see that total profits are maximized when you're both playing high, but that's not Nash equilibrium. So if you're both playing high, then the other team could change strategies and get a higher payoff. So if they're playing high and you're playing high, they're getting 3 million. But if you're still playing high and they switch to playing low, their profits are going to go up to 3.5 million. So they're going to want to change strategies. High is not going to be stable. Therefore, high is not going to be a Nash equilibrium. Now, if you play high and they play low, that's also not going to be a Nash equilibrium. They're happy about their high profits of 3.5 million, so they don't want to change anything. However, you have an incentive to change strategies. Right now you're getting 2.9 million. If you switch to playing low while they are still playing low, you can get your profits all the way up to 3 million. So you have an incentive to change strategies. If you want to change your strategy, then this outcome over here is not going to be stable. Therefore, it's not a Nash equilibrium. Low is a Nash equilibrium. So that involves them playing a dominant strategy and you playing your best response to that dominant strategy. Neither player can change strategy to get a higher payoff. So if you change strategies from playing low to playing high, your profits go down if they're still playing low. You don't want to lower your profits from 3 million to 2.9 million. That's not a good idea. So you don't want to switch. They also don't want to switch. Right now they're getting 2 million. If you keep playing low, but they switch to playing high, then you're going to be over here. That means they get a profit of 1.5 million. That's worse. So they don't want to change strategies either. So if you're both playing low, neither team wants to change their price, so that's going to be stable. That's going to be a Nash equilibrium. Very last case, what if you pick a low price and they pick a high price? So you play low, they play high. That's in this cell over here. That is also unstable. If you keep playing low, they could raise their profits by switching to low as well, going from 1.5 to 2. Alternatively, if they keep playing high, you could raise your profits by switching from low to high. In that case, your profit would go from 3.5 million, shown here in red, to you're getting a profit of 3.6 million. So this is also unstable and not a Nash equilibrium. So unique Nash equilibrium is both teams pick the low price. This is another prisoner's dilemma style situation. It's not quite exactly a prisoner's dilemma. For a prisoner's dilemma, both sides have dominant strategies. Here only one side has it, but it's still very similar in the spirit of the prisoner's dilemma. So again, you'd like to collude. You'd like to have an agreement where you both charge a high price, but you can't collude. And the incentives are, for each team, when they follow their own incentives, it's both charge the low price. So in firms getting these prisoner's dilemma kind of situations, what breaks out is often what's called a price war. They both try to undercut each other's price to steal customers from the other firm and raise their own profits at the other firm's expense. So that can increase competition and lead to outcomes that are still relatively good for society in oligopolies. Now, let's have a prisoner's dilemma game or prisoner's dilemma style game played once. In the real world, however, firms often interact repeatedly. So the other firm doesn't just go away after you play this game once. Next season, you still have the New York Yankees and the New York Mets try to sell baseball tickets, so the game gets played again. Now, if the game is repeated, then sometimes cooperation can occur. I'm going to be vague here. The details are reserved for my upper division class on game theory, so if you're curious, you can go take that class and learn all about it. Under some limited conditions, you can get cooperation. Here's the intuition. So in the game that's played just once, If your opponent doesn't cooperate, then you can't do anything about it. The game just ends. It was played once. If the game is repeated, maybe you can take some kind of action. So in particular, if they cooperate with you in the beginning, you can reward them by cooperating with them later in the game. You can threaten to punish them. If you don't cooperate, then I'm not going to cooperate either in the future. And that'll hurt you, so you're better off cooperating today. Now, to be clear, with firms in competition, this communication does not happen explicitly. They are, again, barred from colluding, but they understand what's going on, and they could figure out that cooperation is the best action. Now, to be clear, this does not always happen. As I was stressing earlier, it only happens under some conditions you get cooperation. You gotta see the details in my other class for when that happens. So sometimes if you try to cooperate, the benefits from that are just not big enough, and the temptation to play uncooperatively, to just take all our customers by undercutting them in price, could just be too big of a temptation, and cooperation could break down. So cooperation might occur, not guaranteed, if the game is repeated.